Hello everyone, I'm Paul and today we're solving problem 2322, minimum score after removals on a tree. Here it says this is hard and this is actually complex, so we'll go from the basics to the solution. There is an undirected connected tree with n nodes. Here you see an example, and we are given this, an array nums and an array with edges. The array with edges contains every edge. So for example, here we see 0, 1. This means we have an edge from node 0 to node 1. Every node here has a value. For example, the value for node 2 is 5. And we are given an array nums which contains these values. So for example, nums at 2 is 5. For example, nums at 4 is 11 in this case. Now we have to remove two edges from this tree. So let's say we remove this edge and this edge. Now we have three connected components. This is one, this is the other one, and this is the other one. And we need to get the XOR value for each of these components. So for example, the XOR value of this component is 11, XOR 4, XOR 5. Now in case you know how XOR works, here we have the base 10 representation for the values in the nodes, and here we have the binary representation corresponding to each value. First we are doing 11 in binary, XOR 4 in binary. And when we are using XOR, if we have different bits, for example here we have 1 and 0, these are different, the result for this is 1. And when we have equal bits, the result is 0. So, given that here we have different bits, the result is 1. Next, we are here. Here we also have different bits, so the result is 1. Here we have different bits, the result is 1. Here we have a 0, so here we have different bits also, so the result is 1. And the base 10 representation of this binary number is 15. So now we have this, and we need to add this part, so we do 15 XOR 5. And first 1 and 1 are equal, so the result here is 0. Next we have 1 and 0, so we have a 1 here. Next 1 and 1, the result is 0. Finally these are different, so the result is 1. And the base 10 representation for this result is 10. So the XOR value for this first component is 10. The XOR value for this component is 1, and the XOR value for this component is 5. And now we need to do this. We need to get the difference between the largest value and the smallest value. And 10 minus 1 is 9. So if we remove these and these edges, we get a difference of 9. And our job is here. We need to return the minimum difference of any possible pair of edge removals. And here the optimal solution is to remove exactly these and these edges. So the result is 9. So basically we are given one undirected connected tree and we need to remove two edges, so we get three connected components, and we need to get the XOR value for each of these, and we need to return the minimum score. And we get the score by taking the maximum XOR value for these three components and subtracting the minimum XOR value. Now the question is, why are we choosing to remove these and these edges? And the answer is, we are trying every possible combination. Down here we have the constraints, and we know that n is smaller or equal to 1000. So we can think in terms of n squared, because this is 1000 square as a maximum, and this is good for us. We can handle this number. So the approach will be the following. Let's say we have the exact same example. Here we have node 0 as the root, that's why it's up here, and now we run a DFS, and more specifically we are running a post-order traversal DFS, and on the way we are storing the XOR value for each subtree. Now, in case you know how post-order DFS works, let's say we are traversing this entire thing from here, from the top and from the left. And we are visiting the nodes that we can touch from the right side. So we come from here and we can touch 2 from the right side. So we visit this one first. We continue. We visit 4 because we can touch this from the right side. Then we visit 3, then 1, and then 0. So as you can see, we are visiting every branch from the leaves. First we visit this, then we visit this, then this, then this, and then this. And we are trying to get the XOR total value at each point. So first we start from here. Here we have no children, so the XOR value that we return here is 5. Now we are here and we do the same. We return 11 because we have no children here. Now we are here and we want to take the value for the children, meaning 11, XOR the current value. And 11 XOR 4 is 15. So we return 15 here. Now we are here and we do the same. We need to do 5 XOR 5 XOR 15. And 5 XOR 5 XOR 15 is 15. Remember that when you XOR equal values, you can cancel this. So the result is 15. Now we are here and 15, this 15 XOR 1, this one is 14. So the value here is 14. So now we have the XOR value for every subtree. We are storing each of these values in an array, by the way. Now we want to run another post-order traversal DFS to find the nodes for every subtree. So we do basically the same here. We start from this side, from the left, from top to bottom, and we visit every node that we can touch from the right side. So first we visit 2, then 4, then 3, then 1, then 0. That's what post order means. And when we are in a leaf, so for example, first we are here, we return a set with the number for the current node. So here we have a set with a 2. Next we are here, so we return a set with a 4. Now we are here, and when we have children, such as in this case, we return a set with the value for the current node, in this case 3, and the values for previous sets. So in this case we have a 4, so we return this. Now we are here and we do the same. We return a set with the value for the current node, 1, and we need to add these 2 and 3 and 4. Finally we are here, so we return a set with the value for the current node, 0, and every value in the next level. So here we add 1, 2, 3, 4. And of course we are storing each of these sets in another array. So now we have all the information we need to solve this here. And we have two possible scenarios. We can split this in such a way that we have nested components. So for example, if we remove this edge, meaning we take this component, we can also take this component, and the XOR value for this inner component in this case is 11, and the XOR value for this outer component is this, meaning 15, and we need to subtract the corresponding value for this subtree. And subtract in terms of XOR is to do 15 XOR 11, and the result for this is 4. So the XOR value for this component is 4. And this makes sense because here we have a 4. And finally we have this component. And the way to get the XOR value here is we do 14. And we need to subtract this subtree. So 14 XOR 15 is 1. And this makes sense because 5 XOR 5 XOR 1 is 1. And the maximum value here is 11, the minimum value is 1, so the difference is 11 minus 1, 10. So the score for removing these and these edges is 10. We can also have a second scenario in which we don't have nested components. Let's say we remove this edge, meaning we take this component, and we remove this edge, meaning we take this component. Here the XOR value is 5, here the XOR value is 15. And the way to get the XOR value in this case is to take the total XOR value at the root, meaning 14, and subtract these two subtrees. So we do 14 XOR 5 XOR 15. The result for this is 4, and this makes sense because 5 XOR 1 is 4. The maximum value here is 15, the minimum value is 4. 15 minus 4 is 11. So the score for removing these and these edges is 11. So these are the only two possible scenarios. We can have nested components or components that are not nested. So with this in mind, we will iterate every pair of subtrees. Starting from here, we remove this edge and we take this subtree. And we can remove this edge, meaning we take this subtree. The XOR value for this inner subtree is 5, and the XOR value for this outer subtree is 15 XOR 5. This is 10, and the XOR value for this component is 14 XOR 15, which is 1. The maximum value here is 10, the minimum value is 1, so the result is currently 10 minus 1, meaning 9. Now we can take the same first component and we can remove this edge, meaning we are taking this component. And the XOR value for this component is 15. The XOR value for this outer component is 15 XOR 15, meaning 0. The XOR value for this component is 14 XOR 15, meaning 1. The maximum value here is 15, the minimum value is 0. 15 minus 0 is 15, which is greater than 9, so we continue. Now we take this first same component and this component. The XOR value for this component is 11. The XOR value for this outer component is 15 XOR 11, which is 4. And the XOR value for this component is 14 XOR 15, which is 1. The maximum value here is 11, the minimum value is 1. 11 minus 1 is 10, which is greater than 9, so we continue. Now we can remove this edge, meaning we take this component. We remove this edge, meaning we take this component. The XOR value here is 5. The XOR value here is 15. And the XOR value for this component is 14 XOR 5 XOR 15, meaning 4. The maximum value here is 15, the minimum value is 4. 15 minus 4 is 11. 11 is greater than 9, so we continue. Now we can remove this edge, meaning we take this component and we take this component. The XOR value here is 11. The XOR value for this component is 15 XOR 11, meaning 4. And this makes sense because here we have a 4. And the XOR value for this component will be 14 XOR 15, meaning 1. This makes sense because 5 XOR 5 XOR 1 is 1. The maximum value here is 11, the minimum value is 1. 11 minus 1 is 10, 10 is greater than 9, so we continue. And now we have seen every pair of components, so finally we return the result, which is 9 in this case. So this is it for the approach. Time and space complexity will be big O of n squared. Now let's go with the code and hopefully you will get the idea. First we say n is length of nums, and we need to create our adjacency list, so we will use a default dictionary. And we will set a default value of an empty array for every key, so we use the word list here. And now we will fill this, so for a, b in edges, adjacency list at a dot append b, and adjacency list at b dot append a. Now we'll go with the first DFS and we will store the value, the XOR value for every sub-tree in an array. So we'll call this XOR, and this is an array with 0 times n. And we'll call this function XOR DFS, and this takes a node and a parent as arguments. And first we say current is nums at node. And now for neighbor in adjacency list at node, if the neighbor is different from the parent, we do current XOR equal and a call to our function XOR DFS neighbor node. And now we say XOR node is current, meaning we are storing the result in the array, and we return current. So now we can call this function with XOR DFS 0 minus 1. Now we can go with the second DFS. Here we are storing the nodes for every subtree in a different array. So we will call this subtree nodes. This is an array with 0 times n initially. And we will call this subtree nodes DFS. And this takes a node and a parent as arguments. And first we say current is an empty set, but this set will include node initially. And now for neighbor in adjacency list at node, if neighbor is different from parent, current union, we show in sets like this in Python. This is union subtree nodes DFS with neighbor and node as the parent. And finally we store the result in subtree nodes at node. So this is current, and we return current. Remember that in post-order traversal we first call this DFS and then we do whatever we need to do. Here we are storing the result in this array. So now we can call this function. We say subtree nodes DFS with 0 and minus 1. And this is subtree nodes DFS. So now we can continue with the result. First, the result is infinity, and we use infinity like this in Python. And now we can iterate every node, so for I in range, but we are starting from node 1 to n because we need 3 components. We can't have any empty component. That's why we start from 1. And we are checking for every pair of components, every pair of subtrees. So we say for j in range from I plus 1 to n. And now if j in subtree nodes I, this is the first scenario. Here we have nested components. So A is the value at 0 XOR the value at I. B is the value at I XOR the value at j. And C is the value at j. Now we can have the opposite nested components. So we say elif I in subtree nodes j. Here we do the opposite. A is XOR 0 XOR the corresponding value at j, B is the value at j, XOR the value at I, and C is the value at I. And this is X. Else, meaning we don't have nested components, A is the value at 0, XOR the value at I, XOR the value at j. B is the value at I, C is the value at j. And each time we update the result, so the result is the minimum among the result and the maximum among A, B, C minus the minimum among A, B, C. And finally, after all of this, we can return the result. So I think this is right. Now let's submit this and see if it works. This word should be sub3, so let's fix this, sub3, and try again. As you can see, this works and this is very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.